Hello, how's it going? I know it's been a hot minute since I did any WebGPU stuff. I just felt like doing it. So today we're going to be looking at sky cubes, basically getting a cube map, getting a sky in the scene. This will be the rasterized stuff. I know I sometimes flip between rasterized and ray traced, but this is rasterized. To start with, I just want to, oh, by the way, this session, some sessions, are line by line. This is how you do it. This isn't one of those sessions because a lot of the modifications that I've made there's a lot of them, but they're very tiny, non-important modifications, and they're not very conceptual. So what I want to do is talk through the theory, then have a look at the implementation, and then you can investigate that at your own time if you wish. So I want to just refresh the theory of bind groups, layouts, and all of that stuff. So imagine that we have a whole bunch of resources, and we want to collect a set of those resources and use them in a pipeline. So say, for instance, you've got your pipeline, you've got your model view projection, transforms, some texture, and a sampler. Okay, no worries. So the pipeline has what's called a bind group layout, and the bind group layout describes the types of things that will be in a bind group, but it has no connection to the actual things which get attached. It just describes the shape of the attachments, if that makes sense. So here we're currently binding bind group 1. However, bind group 2 conforms to the same bind group layout, so at a later point we could switch over to that if we wanted to, and it would all work within this pipeline. If, on the other hand, we make another pipeline which has a different bind group layout, then we'll have to create a new set. Or we could make pipelines which actually conform to the same layout. It's totally optional. So that's just a quick refresher on bind group layouts and all of that stuff, just because it's been a while for me as well. So here's the situation. We are making the sky and then we're rendering the scene. And those are actually going to use two different shaders. They're going to use two different pipelines, but they are going to use the same render pass. When I get to the code, I'll explain how I stitch that all together. But we look at what do we need to render the sky? Well, basically, we need the camera's fundamental vectors. That's the forwards, right, and up vector. We need the cube map, which will describe, it has all the sky images basically, and we'll also need a sampler. Now, these can all be bound in one go because the sky pipeline is only going to draw the sky once. It's a single draw call, just bind everything, draw it. By contrast, in the standard pipeline, some of this stuff gets declared up front. For instance, the model matrices they're a storage buffer and they have a whole bunch of model matrices, mat4s. They are all sent in one go, and then that data is read back as rendering proceeds. On the other hand, the material is basically rebound for each different group of object. So these bind groups have been set up according to the frequency of how often they're being bound and the different things. So this is just an overview of, again, the shape of the resources. If you imagine the flow of resources and how they're being used in the different pipelines. And hopefully that will make the code make more sense should you want to dig into it. But okay, on to the actual stuff. And if you've never dealt with Cubemaps before, that's okay. It's super simple, sort of. A cube map is really a collection of 6 textures. So right now we have this image, but all the computer sees really is literally just a layer of 6 images. 6 of those. Okay, that's what it sees in memory. But a cube map is a little bit more than that. A cube map can also be sampled with a direction vector. So we input a vector, a vec3, and that is interpreted as a direction vector emanating from the origin. And these 6 images are interpreted as 6 faces of a cube of unit length. And when we input that and some direction vector, it performs, under the hood, the graphics card performs a virtual ray trace to identify which face and where on that face we hit. So, okay, that's another thing. So what we need to bear in mind is, okay, given the screen, here's the screen, where are we, where is a given pixel going to hit? And what I like to do, this is an exercise that I like to do when I'm explaining this to my students, is just look at the really basic cases. So if we look right at the center of this screen, this is 0, 0. Okay. And then imagine that you've got a ray coming from the camera's view through that point in the screen. What is that ray's direction vector? Well, that ray's direction vector is just the forwards vector. There's no other component. There's no up, there's no right. Okay. On the other hand, if we were to look over on this side, of course, this coordinate is 1 in the x, 0 in the y. Now, what is the direction vector? We've got the forwards vector plus the right vector. Forwards plus right. Okay, now if we look over on this other side, this coordinate is -1, 0. We say, okay, well, going this way, right? Apologies if this is too simple, but it's the forwards vector plus the left vector, but the left vector is really minus the right vector. Okay, and so on and so on. You can see how this is going. So for instance, if we go up here, that's the top of the screen, y equals 1. That is the forwards vector plus the up vector. And you can see how this is going. So, given some point at random, which has the coordinates x, y, the question is, what is the expression for the direction from the camera that goes through that point? And it turns out, as you can see from these examples, that is a linear combination. It's the forwards vector plus x times the right vector plus y times the up vector. And that's what we do. We just make a linear combination of the camera's fundamental vectors, and that gives us a direction vector that we can use to sample from the cube map. Okay, now we're almost done. We're almost at the point where we'll just look at the code and see what's happening. But before we get to that, there's the question of the depth buffer. So in a lot of cases, if we were doing this in OpenGL, it would actually be very simple to just enable or disable writing to the depth buffer. But when it comes to WebGPU, it's weird, because if it was in Vulkan, we would actually, there are ways to disable writing to the depth buffer in Vulkan. In WebGPU, it's just that awkward point where it's a little difficult. We will probably at a later point when we do post-processing, look at ways that we can actually handle this more elegantly. But for now, I'm going to hack it. And this does work. Okay. So here we have our view. What is it? Frustum. Tangent. Side note, someone pulled me up on this the other day and said, you've got to call it a view frustum, not a view frustrum. I've been calling it a view frustrum for my whole life, and the only reason for that is it rolls off the tongue so much better. If I say view frustum, I get angry. It's awkward, syllable-wise. It's not good. And I really think that's a mistake, and I'm getting a bit sassy here, but people who originally came up with that word, they goofed it. All right, so, back on point. How do we fake the depth issue? Because if we were to draw this on the screen at a depth of 0, that would actually be drawing on the near plane. Okay, so drawing the screen shader does its thing, but then if we render the scene back here, it'll be covered by the screen, always. So what we actually want to do, so say this is z equals 0, depth equals 0, this is the far plane, depth equals 1. What we actually do is just render to the far plane just by setting the Z coordinate to 1. And that makes sure that what we draw to the screen is physically behind the scene when we go to render it. But I've talked enough. Let's have a brief look at the code. Okay, so here we are in the code. I guess it might be a little simpler to start with the shader. So I'll just put this off to the side. Maybe I'll just focus on that. Okay, so we're going to take a few things in. We're going to take in, we've got this struct which describes all the fundamental vectors of the camera. Then here we describe our bind group, the bindings in our bind group. Just like I was saying on paper, we have the camera vectors, the sky texture and sampler. Okay, no worries. And what we want to do is when we run the vertex shader, we want to write out onto the screen, of course, but we also want to output the direction vector so that that can be used in the fragment shader to see the sky, basically. Now, we could send through a vertex buffer, but what's the point? Because all we're doing is rendering a screen-sized quad. So I'm just defining these positions. These will cover the corners of the screen. And then when we go to run this, okay, no problem. We write out the position, make sure to write out z equals 1. That puts it behind the scene, not in front of it. And then we perform this trick with the linear combination of the forwards, right, and up vectors. Okay, making sure to normalize that. It makes it a little stabler. It doesn't really matter. Doesn't make a difference. I'll stop rambling. Okay, and then we have this fragment shader. All we take in is a direction, and we can just use that the same way you would use a standard texture coordinate. Because this is a cube map, it will sample from it correctly. So it's probably a good idea for me to just run this and verify that it's working. We go, it is in fact correctly rendering. Okay, so again, just to really reiterate it, there are two pipelines working at the moment. The sky pipeline runs first and it samples the sky and draws it onto the color buffer, but it draws it right at the far plane. So everything that gets drawn after that will overwrite it. And that's what we're doing here with the standard pipeline. There we go. Okay, excellent. Let's close that down. Now, just to verify the difference this makes, I'll switch that to the near plane and there we go. And if we were to render this again, we can see that, yeah, that's what the cube map is doing, but it's covering the scene. So not so great. Okay, now I guess the next part to look at is the cube material. So we'll go down, there's this cube material class. Now remember that really a cube material, the computer just sees 6 textures. So that's what we're going to do. We'll take in an array with 6 strings, so the 6 different file names. And then we'll just loop through, and for each of these, we will basically load in the texture. And I guess the important part here is when we go and create the view descriptor, we need to specify that it's a cube. Okay, quick little side note. I heard some people saying that they were having trouble with tsconfig not recognizing types. I actually had the same issue and I found a fix. I'm not sure if this is a proper fix or just a me fix. So let me know if this fixes the issue for you. But what I had before is I had this types, WebGPU types, and it's complaining up here. It's saying, cannot find type file definition. Can't find it. And in fact, if we go over to like the renderer, for instance, now it's not recognizing any of these types. It still works, but we don't get autocomplete, and that's really bad. And I found all I needed to do was comment this out. Truth be told, I'm not really sure how that fixes it. So do let me know if that does or doesn't fix it. It's important. But anyway, where was I? Right, okay, so we create the view descriptor. Yeah, no worries. This is important here as well, array layer count. So there are two things we use when we're configuring textures. That is levels, like if we have MIP maps, and layers if we have a whole bunch of images. And that's what, it's just 6 slices of image, if that makes sense. So yeah, I mean, I'll leave this for you to look through in your own time. The only thing I will really highlight here as well is when we go and copy the image we've loaded into the texture, we need to set that with an offset of 0, 0, x and y, but with an offset, a varying offset in the z. And that'll make sure that it gets copied to the correct layer. But yeah, just leave that. Now if we go over to the renderer, I'm falling into the trap of talking through my code one line at a time. I'll try to avoid that. Yeah, I'll get to the important stuff. So, okay, you can look through this in your own time. It is important, but it's boring for me to talk through. This part here, this is pretty important. So, I shipped all of the bind group initialization stuff to this prepare scene function. Here we set the view, projection, all that stuff, but we also write the fundamental vectors. Now, if you haven't been following my ray tracing series, this bit might be a bit confusing. We're setting a bunch of vec3s. What's with these extra zeros? Well, that comes down to memory alignment. So on the GPU side, it's really just expecting to see vec4s, because if you have vec3s, then it can sometimes be wasteful to grab data. The GPU will really only grab, think like a float, 2 floats, or 4 floats at a time, depending. And so when we declare a vec3, there's actually implicit padding. So if we don't put in these extra zeros, it will, like if we did this, it would grab the first 4 floats here, and then ignore this 4th bit, set this as the forwards vector, and then when it goes to grab the right vector, it'll go 1, 2, 3, 4. So we got that, and we get what I call data drift, basically, which isn't good. So implicit padding, it would actually be better just to have everything as vec4s. But yeah. So then there's this stuff with dy and dx, and these are basically correction factors. So up above, when we created the perspective projection, we had a field of view y angle as pi on 4 or 45 degrees. So we can think of that, I'm just thinking, we can think of that as like the what am I thinking? Or just think of it as the lens angle as the lens opens up above and below. So if we are opening up 45 degrees, then the upper end is 22.5 degrees and the lower end is 22.5 degrees as well, half of 45. But this correction factor just makes sure that the sky map, the sky cube, will drift appropriately to track the camera's motion. And then similarly, what we do is we take that dy dz, basically, multiply it by this correction factor to get basically how far to the left and right we should be going. Now, just so this makes sense, if I were to get rid of all these correction factors, because this is logically what we'd think, right? Send the camera's fundamental vectors. Well, let's go and run that. Okay, so here we go, here's the scene. But then if we look here, it looks a little funky, right? So I'll go back to, at the start I had this sort of thing. Whoops, get up. Okay, so we look up, look down. it just doesn't look right. And what you'll find is that we are looking the right way. Okay, so if I look up, yeah, we're looking up. We're looking down, left, and right, but it just isn't quite tracking what the scene's actually doing. And the reason for that is that this is implicitly basing the whole thing on a few things, on a perspective angle of a field of view Y of like 90 degrees, I guess, and it's not correctly accounting for the aspect ratio of the screen. So if we go up and down, it looks a bit squashed. It's not good. And that's basically what this dydx is accounting for. So if we just put all that back in, put all of that back in, and then give that a go, we will now find that the view and the camera are locked to the same underlying projection. They're moving the same way within reason. So yeah, I mean, that was it for today. I hope you had fun. It is bothering me, the flaw, a little bit. So I want to look at MipMap stuff. Now, as far as I can tell, WebGPU doesn't have a default way of making MipMaps, and everyone online is getting sassy and saying, why aren't you making your own MipMaps offline? So I guess I'll have a look at that. But yeah, anyway. Yes, yep, that'll be it. So yeah, thanks a lot. Have a great one, and I'll see you again soon. Bye.